Okay, so let's talk about a lower bound on the extremal number of complete bipartite graphs, which, if you recall, last time we were talking about extremal numbers and we gave an upper bound on the extremal number of complete bipartite graphs. In particular, we had this one. So let's try for a lower bound. So if you recall, this extremal number, it means the largest number of edges in any graph that has n vertices that does not contain KRR as a subgraph. So what we need for a lower bound on this is we need a construction. We need to show that there exists some graph on n vertices with some number of edges that doesn't contain k sub rr, and then the extremal number is at least however many edges that graph has. So we'd like that to be as many edges as possible. So here's the idea. We're going to use the probabilistic method. We're going to consider a random graph. It's going to have n vertices, and each edge is going to be present with probability p. So you have all of these possible pairs of vertices that could be an edge or not, and each one is an edge with probability p, and we do that independently. Now, we could just do that and just hope that the random graph generated doesn't contain any k sub r's. If p is small enough, then there should be very few edges, and the probability that these very rare edges are going to somehow come together and make this specific subgraph would be small. However, that's not what we're going to do. We are not going to rely on the random graph G not having any k sub r's. What we're going to do is we're going to generate the random graph G, and it might contain some k sub r's. But then we're going to change the graph G. And we're going to do it in a very simple way. I'm going to find any k sub rr subgraph and just remove an edge. I don't even care which edge, just remove one edge. Of course, it's possible that I would remove one edge and that would kill more than one k sub rr, but I'm just going to remove I'm going to remove edges until there's no k sub rr's left. If I see a k sub rr, I'll remove an edge from it, and then I'll look around to see if there's any more, and then if there is, I'll remove an edge from one and repeat until there are no more. So that's the plan. By doing that, I will definitely generate a graph that has no k sub rr's, because I'm just going to keep removing edges until that's the case. So let's talk about how many edges are left, at least in expectation. So let x be the number of edges in G. Then the expected value of x is n choose 2 times p. And maybe this is going a little bit fast here, but let me justify this. This is just another one of these, I can write x as a sum of indicator variables. So x is the number of edges. So I would sum over all possible pairs of vertices uv. And what I would do is I would sum the indicator variable that says uv is an edge, and that would count all of the edges, and you would add those up, and so x would be the total number of these pairs that are edges. Then I do expectation of both sides. So when I find the expectation of x, and then doing the expectation of this is easy. First of all, there's n choose 2 terms because there's a term for each pair of vertices, and there's n choose 2 pairs of vertices. And then the expectation of a indicator random variable is just the probability of the event underneath. We went over that last time. And the probability of this event is p. The probability of any particular pair being an edge is p. So that's the expectation of x. It's n choose 2 times p. Now, I need to talk about the number of edges that are going to be removed from this graph, because I already have the expected number of edges that we would start with, but then I'm going to remove an edge from each case of RR. So I need to talk about how many times I would need to do that. So I'm going to let y be, essentially it's the number of K sub RR subgraphs. And I phrased it this way. It's the number of pairs of sets R1 and R2 such that these are 2 sets of R vertices each. Maybe I should emphasize they're disjoint. Basically, R1 and R2 are meant to be the 2 sides of a K sub RR, right? So it's 2 disjoint sets of little r many vertices each, with every possible edge between R1 and R2. So y is just the number of pairs of sets like that. So let's find the expectation of y, and we can do this the same way because y is the sum of indicator variables. Y would be a sum taken over all possible pairs of sets R1 and R2, where you do the indicator variable with the subscript just stating that G has every edge between R1 and R2. And you add those all up, and that would be Y. And we can do the expectation the same way. First of all, every single term is the same, and the number of terms is just n choose r times n minus r choose r. That's the number of ways to choose a set of size r to be R1, and then from the rest of the vertices, the rest of the n minus r vertices, you choose r of them to be R2. And then the expectation of an indicator random variable is just the probability of the event underneath. And this event has probability p to the r squared because this is the event that we have every edge from R1 to R2. And right, the number of possible edges would be r squared, and each one is with probability p, and they're independent. So the probability that all of these r squared edges are there would be p to the r squared power. Okay? So the idea for the proof is as follows. In the end, we have at least this many edges because, once again, what are we doing? We're generating our random graph, and then I'm removing one edge from each case of RR. And that, as we discussed, it's possible that I'll remove an edge and that'll destroy more than one case of RR. But the number of edges that I remove in this process is at most the number of K sub RRs. In other words, it's at most Y. So I generate my random graph, I have X many edges, and then there's the edges that I remove, which is at most Y many edges. So the number of edges remaining is at least X minus Y. number for remaining edges is at least x minus y. And the expectation of x minus y, again, by linearity of expectation, it's just, here's the expectation of x, here's the expectation of y. This is at least, say, this, and this inequality is for again, it suffices to show this for sufficiently large n. Of course, n choose 2, it's n times n minus 1 over 2. That's roughly n squared over 2. So what I did here is I replaced this, which is roughly n squared over 2, I replaced it with n squared over 3. And then this inequality is valid for sufficiently large n. For sufficiently large n, n choose 2 is bigger than 1/3 n squared. Also, I'm using some simple inequalities here, like n choose r is at least, or it is at most, yeah, it is, yeah. It is at most n to the r over r factorial. And this is also at most n to the r over r factorial. So I got n to the 2r over r squared factorial here. Now, we haven't really talked about what the value of p should be. And when you do a proof like this, it's generally a good idea to keep your parameters, keep them general until you see what you're going to get, until you get to this point, because this is valid for any p, and what value of p we plug in basically determines how good of a result we're going to get. So what are we doing here? Basically, this is going to be our bound. This is going to be our lower bound on the extremal number, because this is the expected number of edges that are left in this graph that we're producing that we know to be KRR free. It doesn't contain KRR as a subgraph, and this is the expected number of edges in that graph. So we're showing by the probabilistic method that there exists a graph with this number of edges that does not contain K sub RR. And then we choose P in order to optimize this. We would like the best possible lower bound, so we can choose a value of P to maximize this. And I didn't really choose a value of p that absolutely maximizes this, but I chose a value of p that, well, I just didn't want to, there should be a coefficient here to like completely maximize this. There should be some coefficient, but this is the correct power of n. Basically, if you plug this in, this term and this term are somewhat comparable. You get, both of them are on the order of n to the 2 minus 2 over r plus 1. And it's just this term has a smaller coefficient than this term. Anyway, you plug this in and you get a constant, and this constant depends on r, but it doesn't depend on n. You get a constant times this power of n. And that's our lower bound on the extremal number of KRR. So just to review, we got upper and lower bounds on the extremal number of KRR in general. Our upper bound was a constant, and I'm not being too picky about this constant, so I just wrote a big C, times this power of n, and our lower bound was some other constant times this power of n. So it's not even the same power of n. And there's a lot of interest in graph theory and combinatorics of determining the order of magnitude, because this is a function of n, like for fixed r, this is a function of n. And we have it sandwiched in between this power of n and this power of n, but they're not even the same power. And as we know, if you're comparing two powers of n, the bigger power grows much faster than the smaller power, like for k equals 5. What this tells us is that the extremal number is between something on the order of n to the 9/5, so that's n to the 1.8. This is 1.8 in the exponent. And then on the lower bound, we have this, which is like 1.666. So they're not too far off, but they do disagree. And, you know, n to the 1.8 grows much faster than n to the 1.666, right? So this is, in a sense, this is still wide open. And by the way, this is essentially the best known. This isn't quite the best known. Somebody managed to prove a slightly better lower bound that has like a logarithm of n, like it's multiplied by log n or something, like a power of log n. But that's still not very significant. N to the 1.666 times a power of log n is still much, much smaller than n to the 1.8. So yeah, this is a wide open field of graph theory. And so next time I will talk about some of the smaller values of r, because this that we went over, at least for large values of r, and not even that large, like r equals 5, this is essentially the best known, except for, as I discussed, there's like a logarithm, but this is essentially the best known. For smaller values of r, this is not. For smaller values of r, we know better. Like r equals 2 is actually, we have a very satisfying and nice answer for r equals 2 that I'll talk about next time. All right.